where are we? Fields, isn't it?
Mm-hmm.
Fields, and it's the last lesson, Kepler. Okay.
T formula.
The what?
T formula.
Kepler's T.
Yeah, I want to check my formula. I think
T squared equals 4 pi squared over gm
okay.
or cubed.
4 pi square.
Yeah.
What do you use the T formula for?
Find T, of course. What else did you use the T formula for?
For mass.
Do you know how to find T?
For mass.
Yeah,
Do you know how to find T?
we have to find mass.
Yeah.
Mass of what?
Let's do it now.
Mass.
Of
Mass.
oh, that's the beginning.
Yeah,
Okay,
mass.
okay, yeah.
Wakey wakey.
Yeah, I see this, yeah, I see this.
Okay. Why isn't this writing pad turning on? Come on.
I think your information is wrong.
Which one?
The one you gave us to us in the questions.
No, I think it's correct. No,
What you got? What's the answer?
mass
Mass.
1.68.
No, that's wrong. I checked on Google.
Actually, I checked Google.
It's
It was
6.29.
no,
Yeah.
it was if like one decimal place wrong.
Simple. I'll just check it as we make the answers.
Yeah,
Ah, now the writing pad's
it
working.
was one decimal place
We
wrong.
just chillax, everybody, chillax. Let's have a look here. Right, so the first question was estimate the mass of Mars. So 1A, you've got Mars, and you've got its moon is traveling around Mars. We know the radius here, and we know the time. So let me see. The radius 5989. 5989000. What?
It's 6.29.
For what?
The mass of Mars.
I haven't calculated the mass yet.
No, I'm checking.
Oh, yeah. Well, hold on. This is the radius, and then the time is 7.65 hours.
Mm-hmm.
So that's 7.65 times 3,600 seconds.
Yeah.
Kepler says that T squared equals 4 pi squared over g m
RT.
or cubed. So that means m would be 4 pi squared over gt squared, not to be confused with GTA.
You wrote it wrong. It's cube. There's a cube on R and the square on the pi.
Oh yeah, where did my square go? Fell off. Right, 4 pi squared or cubed, and the or is 5989000. The g is 6.67 times 10 to the minus 11, and the time squared is 7.65 times 3600. So I got as the mass 1.68.
Times 10 to the 23.
Hold on, before you start making claims about right or wrong, let me check. So let's just open up. Now, if this was a real exam question, you would get full marks here. If the mass is not actually this, it means something in the question was wrong, like maybe the time of the orbit or something. But let me check it.
No, not mass of folks, mass of
Oh,
Mars.
sorry, mass of, typed the right thing in. Mass of Mars.
You can Google
Will
it.
Google give me
Yeah.
it directly as a result? Okay.
Yes. And this is open Google.
Mass of Mars. 1.6. Okay, it says 6.39. So it's the right order here, 10 to the 23. So let me just see, what did I give you? The time of
Orbit of Phoebus.
orbital period, 7 hours and 39 minutes. I said
65.
7.65.
Is that accurate? It's quite small.
That's a bit small.
It might actually, because you're squaring it.
And then multiply by 360 and 260.
I'm gonna try that.
I think it could make enough of a difference. So it should be 7. What? No, no, no. 7. No, no, no. 7 hours and 39 minutes. Is that what I said?
No,
No,
it's gonna be less.
yeah, it's gonna be less
Hang
seconds,
on,
like
hang on, hang on.
25,235 seconds.
7 hours and 39 minutes is 7.65 hours.
Right.
Yes.
So, okay, so that's correct. What else did I give you? The distance between Phoebus and Mars. So, what did I say it was?
5989 kilometer.
Kilometers.
Hmm.
No, actually, maybe this is where the problem is. Because I hear it says it's 9380.
9.
What did I say?
5989.
I guess the website I got it from was wrong.
Maybe you wrote it.
No, no, because I would have copied and pasted it from the web page.
Okay.
So, at only 17 miles an hour. Okay,
9380. Let's try this.
9380 then.
Three.
So almost all my answers are wrong.
No,
Nine.
no, no, I'll continue with the numbers I gave you. Instead of being Mars, we can say a planet in a solar system. And instead of saying Phoebus, we can say a moon around a planet in a solar system. Yeah. But for next students, I'll change the distance to... Okay, so if you change that to 9, would that fix it up?
Most likely.
9380. 6.44.
That's new.
Yeah. But I'm going to continue with the numbers I gave you. And instead of saying Mars and Phoebus, I'll say a planet like Mars and a moon like Phoebus. Alright, what's the next part?
The velocity.
Right, so that is F equals mv squared over r, and F equals gmm over r. So that means mv squared over r equals gmm. Mv squared over r is or squared here.
Yeah.
Mv squared over r equals gmm over r squared. The small m's cancel, one of the r's cancels, and the v will be the square root of this.
Which am I going to use?
Mass of Mars-like planet. Mars 2, we'll call
Why
it.
that one?
Because it's the big M. Because the small m cancels with the small m, the mass of the moon. So I have it on my calculator. So square root answer times 6.67 times 10 to the minus 11 over, and I'm using for this question 5989000. No square though. What velocity did you get?
1367435.
Really?
Yes.
Oh, sorry, my answer, I should be using the other math. 1.68 times 10 to the power of 23. 1368?
Yes.
Yeah. Okay, C part.
The two radius give me that 10%.
10% of the variation.
The two.
Yeah, so what's happening here? Come on.
This was very hard.
And let's say here is Mars. So this is when it's at its closest. yeah? And this is when it's furthest away, and this will be some point on average during it. So the average velocity is 1368 meters per second. So I'll call this v. Here, when it's further away, will it be going faster or slower than v?
Slower.
Slower than v. And then here,
Faster.
it'll be going more than v. And the radius on average is 5989. Yeah.
Yeah.
But at this part,
More.
it's an extra 10%. And then for this part here, it's minus 10%.
Hmm.
That's what I was picturing.
Can vary by up to 10%. What is the faster than this?
Yeah. Now, you remember when I did this last time, it was a bit of a pain of a calculation. Let's see if we can approximate it. I don't know if this will work. I'm just going to have a look at the side, see what happens. So, what I'm thinking is here, if we do the time per second, here is radius 1. This distance it travels here, which we'll call x1, that will be equal to v1, because per second. If I said it's going 500 meters per second, then in 1 second, how far has it travelled? 500 meters. So as long as my units are in the same unit as the area, guys, can we look up? As long as my units are in the same unit as the area, then the distance will be v1 here. Is that okay? So like if the v is 500 meters per second, then in 1 second, this distance here is 500 meters. Yes? So if I draw my triangle, let's draw it again. This is this is V1, this is R1, this is R2. And then later, when its radius is different, or smaller, sorry, it's R1, R1, this is R2, R2, and this will be V2. What you know is that the areas here are the same.
But V1 and V2 are not same.
And they're not the same. Like R1 and R2 are not the same. So you know that the area 1 here is the same as area 2. So we can say area 1 equals area 2. Now actually in maths, from semester 1, in the trigonometry lesson on areas, I gave you a formula at the end of page 58 for how to calculate the area of an isosceles triangle, which is the type of triangle you have here, with base B, length R1 or B, and base A. So that's exactly the type of problem we have here. So rather than reproving that formula, I'll just use that formula here.
Can you draw this one?
Yeah, I won't remove this from the screen.
Which angle are you going to use?
No angles, just using the length. So according to this formula, area 1 should equal a half R1 squared square root the base, which will be V1 squared over R1 squared minus a quarter. And area 2 will be a half R2 squared square root V2 squared over R2 squared minus a quarter. Yep. So remember the time interval we were looking at is 1 second. So we know that area 1 equals area 2, so a half R1 squared square root V1 squared over R1 squared minus a quarter, that should equal a half R2 squared square root V2 squared over R2 squared minus a quarter.
Okay.
Yeah. So I can cancel the halves like that. What else can I do? Yeah, let's see. Now, did I write something down wrong? B squared.
You're looking for, you can put the values in,
Yeah, I'm just want to make sure I didn't write anything. Common side B, which is on the top. Oh, I think I wrote my fraction upside down.
Oh.
Base. Yeah, sorry. You can change this. It should be R over V. It's on the formula. So I'll just change it on this line. Well, I'll change all of them. R over V, R over V, R over V, R over V. And of course, I've mixed up my R's and V's, so it's not R2, it's V2, V1, and here is V2, and here is V1. Okay, now it's fixed. I'll give you a moment to fix that. Okay. Yeah, the R on the outside should be a V. Okay, now this formula is still quite messy and difficult, so let's simplify it. Let's look at the inside piece here. Have a look here. What's up? No, look up. I'm not going to remove anything off the screen. So if I look at this inside piece here, or big or small, the radius, big number or small number?
Big.
Big, very big, like 10 to the
Million.
millions, 10 to the 6, 10 to the 9. And the V here is also pretty big, but not as big, maybe like 1,000 or 100. So this number here will still be in the millions. If I have a number that's about a million and I take away 0.25, will I affect the value much? No. So this quarter, I can drop it. It's not going to change the value much. So I can write this now as a half V1 squared square root R1 squared over V1 squared. Oh, sorry, the half is gone. V1 squared square root R1 squared over V1 squared equals V2 squared square root R2 squared over V2 squared. So now I get V1 squared R1 over V1 equals V2 squared R2 over V2. But of course, the V2 cancels with the power and the V1 cancels with the power. So you get this very nice formula, much nicer than what we did last time. V1 times R1 should equal V2 times R2.
R1 squared. Okay, the square point.
I'll just go down to this far. Is that okay, Fahad?
Yep.
Yeah. So you could say that the velocity at the second location is equal to R1 over R2 times the velocity at the first location. So in the question, I'll go back when you're ready, just let me know.
You
Yep.
forgot to put square in this, the square root.
Square root where?
You know the V2?
Yeah, those constant. Line number.
Oh yeah, I forgot to write the square here.
Yeah.
Yeah.
You can put this
Mhm.
from there.
Yeah. Yeah. So actually, when you look at this, this is very nice because if I say that the radius has decreased by 10%, what will R1 over R2 equal as a fraction? If R1 is 10% smaller than R2, what will R1 over R2 be?
The average.
No, come on. I say R1 is 10% smaller than R2. Or sorry, or is it the other way around? R2 is 10% smaller than R1.
You can divide the 100 multiply.
Yeah, no,
Yeah.
you're complicating things. Don't complicate things.
10.
No.
90?
No, not 90, but you're closer with 90, but still way off. Let's say R1 was 100 meters, yes? And R2 is 10% smaller, so that's 90 meters. So what's 100 divided by 90?
0.9.
It's not, 100 divided by 90 is not 10. And you know it is not, KJ. It's like, no it's not, because 100 divided by 90 has to be more than 1 because the bigger number's on top. Just stop being ridiculous and calculate it.
1.111.
1.11. So, if I go back to the question here, this velocity here will be 1.11 times the velocity v, and this one, which is 10% smaller, will be 0.9 times the velocity v here. So your answer should be 1368 times 1.11. So you should have 1518 meters per second, and the other one, 1368 times 0.9, you should have 1231 meters per second.
This is the big minus 10% is plus.
This one here is the one which is 10% smaller radius, which actually matches up to 11% increase in speed.
One five one eight. I didn't get that. I got 1504 and 1505.
What? What did you get?
1505.
For which? The faster one?
Yes.
Fine. Fine. 1505. That's fine. Oh, yeah. Can I go to the next one? D. What is the density of Mars, or our Mars 2.0? Density is mass over volume. What did I say the mass was earlier? It was 1.68
Times 10 to the 23.
times 10 to the 23, and the velocity, not the volume 4/3 pi. Now, did I say the radius of Mars?
Yeah.
The of Mars.
Yeah.
What's the radius? 3,390.
Yeah.
3,390,000 cubed. So before I calculate, I should have a rough idea of what type of number I'm expecting. What's the density of water in kilograms per meter cubed?
1,000.
1,000. Do you think Mars is denser than water or less dense than water?
Denser.
Yes, since it's a rock. Rocks tend to sink, so it should be denser. So I would expect something in the region of 1,500. Let's see what I get. 1.68 times 10 to the 23 over 4/3 pi or cubed 3,390,000. Okay, not as much as 1,500. 1,029. Unless I typed in something wrong here. 1.68 times 10 to the 23 4/3 pi or cubed 3,390. Yeah, what did you get?
1029.
That's what I got. Not what you got, KJ? One. So this is telling me that Mars is only slightly denser than water.
Oh.
What did you
Is
get?
it our values or no?
Huh?
Is our values or no?
This Mars-like planet is only slightly denser.
Okay.
Yes. Well, the math is wrong.
Yeah.
If this was because if this was a planet like Mars, I made its mass smaller. I should make its radius smaller as well. Yeah. It's still good that it's more than 1,000 though. At least my planet is possible. So actually, my planet here that I've made up, we won't call it Mars. We'll call it the Stephen planet. It's only slightly denser than water, so actually it's still a solid planet, but it's not too far away from being a gas planet, like Jupiter. You know what I mean?
So Jupiter is not dense.
I don't know, like Jupiter's a gas, so I would have thought its density is less than 1,000. Because 1,000 would be liquid water.
The entire planet is gas.
Jupiter is, yeah.
Yeah.
The gas planet, yeah.
The entire
The
planet.
entire planet, so you can't land on Jupiter because you'll sink to it, through it.
You can pass through.
Uh,
It's a gas, then you can pass through.
well, if your ship is strong enough, I suppose you could, but I wouldn't recommend it. No, Jupiter is a gas planet, so and so is Saturn. So you couldn't. I don't think you could actually land on them. Your ship will just sink through the gas. Yeah. So I'm saying I'm glad that I got more than 1,000. It means my planet is at least a solid. I could land on it, which is good since it's named after me. Right. What is the gravitational field strength on the surface of Stephen's planet? So the formula is G equals GM over R squared. Right, so what is the M? 1 point, what's the M?
1.68.
times 10 to the 23.
Okay, and the radius? Oh, I have it there, 3,390,000. So the G is quite a low value, 0.975 newtons per kilogram.
You can count flutes.
No, but I mean, it's not even 1 meter per second squared, so it means like, it's like you're 10 times lighter, so you could jump 10 times further. Yeah, sounds nice. Right, so that's E.
But in moon you can do like this moon.
Moon will be about,
1.6
yeah, about 6 or 7 times lighter, yeah. What is the parking orbit for the probe around Stephen?
Oh, okay.
No, I did give it a better name than Stephen. Needs to sound like a Greek or god or something like.
Steeples.
Yes. Stevos. Yes. This I can live with. Right. Stevos. Yeah. So F here is the parking orbit. So the trick here is the time. What did I say the time was? How many?
7.65.
7.65 times 3,600.
Mhm.
So that's 27540 seconds. Yep. Now what formula can we use to get the radius? Well, we know the time,
Mhm.
so I guess we could just use Kepler's law again.
Yeah. Three
That
roots.
that says t squared equals 4 pi squared over gm or cube. So yeah, or would be the cube root of gm over 4 pi squared. Oh, and there's a t squared down below as well, isn't there?
It's up.
No, yeah, sorry, it's up here. T squared here. Time squared divided by 4 divided by pi squared times g times the mass of Stevos. So that is 1 point. What did the mass was?
1.68 times 10 to 23.
Right. So I got a huge number.
Number.
Huge number.
19
Ridiculous number.
198463.
10 to the.
Nothing like that.
Oh, let me double. Oh, hang on, I forgot to cube root it. Right. So answer cube root.
599.
Yeah. Okay, that's a bit better. If I put it in kilometers. Actually, that's not too big. It's 6,000 kilometers about.
Yeah.
Now, that's actually okay. It's nearly 6,000. I'm going to round it up to 6,000 kilometers. Actually, that's not too bad. So the planet here, what's the radius of the planet? It's 3,000. 3,390 kilometers,
Yeah.
and the park in orbit would be 6,000 kilometers. So the height above the surface would be 6,000 minus 3,390. So you would need an altitude of 2,600 kilometers. Is that okay? Do I ask you for the height above the surface?
No. But I think we might need it in the next question.
No. Oh, I'm going to change this to height to make it a little bit more difficult.
What's that?
Why?
Because in just
Next time.
for next time, yeah.
Yeah.
Right. What is the field strength? So what value am I expecting here? Like what size of a number? Less than
0.9.
0.9. So maybe 0.5 or even less.
By far less.
So G equals GM over R squared. The radius is 6. 1, 2, 3. 1, 2, 3. And the mass 1.6. No, it's the planet.
Oh, no, it's
No, I'm 100% sure it's of the planet it's orbiting.
Mhm.
Or is it the planet or the moon?
The planet.
Yeah.
okay.
6,002.
Not as small as I thought.
This is the mass
0.311.
of what?
The
Mass of planet?
Stevos.
1.6.
Yeah.
That was 100 kg you used.
No, I just was explaining to him. No,
Why didn't you use the mass of the
Yeah.
thing? The
because that would be wrong. I used the mass as the thing that's making the gravitational field. The space probe is only 100 kilograms. It has no gravitational field. The planet is the thing making the gravitational field. I should use that.
So the number is big.
No, it's not. I got 0.3.
Yeah.
What did you use for R? Whole squared.
599.
0.31.
Yep.
Yeah, going to.
What is its potential energy while it's in this parking orbit? Potential energy would be a negative number, G M over R, not squared.
Why did you put absolute?
I just want to make it clear that it's a negative number.
Absolute, the value.
And this thing here, come on, read fully please. Right, so 6.67 times 10 to the minus 11 times times 1.68 times 10 to the 23.
The small m is now what?
100, yeah. And the radius is 6,000 kilometers. If I do this in mega, 187 minus 187 megajoules. I'm going to add in an I part here.
No, go on.
So my I part I'm adding in here is what is the total energy. So total energy is equal to kinetic energy plus potential energy. Kinetic energy is a half 100 v squared minus 187 times 10 to the 6th. Now, do we know the velocity of the probe?
Who's that?
I got minus 187, no? Megajoules.
My
Yeah,
number is too
13.
big.
What?
No, no.
11368.
You used radius 599.
6,000, yeah. 6,000 kilometers.
It's the same thing, the same thing.
Yeah, but it is actually the same thing. It is in kilometers.
No, no, I convert into meters, you know
No.
this.
And you multiply in the small you 100 kg.
Yeah?
I got 1.86 times 1042.
Did you have in your G?
Yeah.
Minus 11? You
Yeah.
must put minus 11. It sounds like you put in plus 11.
Mm-hmm.
Let me see.
I'll put 23 here.
Yeah? Continuing now. Right, so, we have a formula to calculate the velocity. I won't rework it out, but the formula was, where's it gone? Root G M over R. Yeah?
Velocity of what?
The probe.
I thought we already knew that.
Did we work it out?
One.
Or I thought that was the velocity of the moon.
No. Oh yeah.
Yeah. Come on, focus. Wakey. So velocity of the probe is root G M over R. So that velocity will be root 6.67 times 10 to the minus 11 times times the mass of the planet, 1.68 times 10 to the 23, and the radius of the probe is 6,000 kilometers. So I got a pretty fast 1367 meters per second. So if I pop that in there, I can get the total energy.
It's the same thing.
As the moon?
Yes.
I think that's just a coincidence.
There's no way any one of them will change. Okay, it could be the because the radius is like the same thing with the moon, I guess. Okay.
Hang on, I get confused. This is the probe around the planet. Oh, what's the distance from the... No, that's not the same.
It's not the radius cannot be 6,000.
No, it's not the same.
What's the radius?
that's the distance from the center of Mars to the moon.
Oh, have we not worked out the radius? Oh, it's the parking radius.
Mhm.
Yeah, 6,000. Was that the parking radius?
Yeah.
Yeah.
What do you got? I got different answer. Minus 935
For what?
for this.
For the speed?
Yeah.
How'd you get
No.
negative?
No. This put for the total
No, I haven't
negative.
worked out the total yet. We're back at a step here where we're not sure about the velocity. Right, hang on. This is the probe around Mars, isn't it?
Yeah. No, Steve.
Stevos, yeah, and the mass is 1.68,
Yeah. Times 10 to the 28.
or am I using, that's my answer from part A. Yes. And the parking radius is 6,000.
Yep.
So, how come I got the same answer as the velocity of the moon? Which one was that?
They don't have the radius same, right?
Mhm. Number B.
B here.
If you minus the distance from moon to the planet, it's 6,000.
Is it?
Yeah.
Ah, so I think it's just a weird coincidence then that the moon is in a parking orbit, like the probe. It's just a weird coincidence that both the moon and the probe are both in a parking orbit of the planet.
Oh yeah, because you used the wrong distance. You know the normal distance was meant to be 9380.
Yeah,
So we did not change that.
And
yeah,
because the radius is different.
yeah. What do you mean in the normal
Like
distance?
the distance, like the distance you gave us.
Yeah.
You know you check Google again.
Yeah.
Yeah.
I'm using that distance.
You
Yeah,
gave
yeah, yeah, yeah,
1 0.
yeah.
Yes,
So
exactly. That's why it's the
in
same.
this imaginary planet and moon, the moon is actually in a parking orbit, which is weird because it means the moon is always in the same place in the sky when you look up. So what do we say the orbit was? 7.65 hours?
Yeah.
Yes.
So then that must mean that the planet uh, has a day of only 7.65 hours. Yeah. So that's just a weird coincidence that the moon and the probe are both at the parking orbit altitude. So it's a weird coincidence, that's all. You're giving me the total energy. I haven't calculated yet.
It's minus 9356 triple
A
five.
half m v squared minus 187 times 10 to the 6. You got a big negative number?
Yeah.
So what did you get? Minus,
935
yeah,
555.
minus 93.6 megajoules.
Why is it minus?
Because the potential energy is so negative, it's quite trapped. If you wanted to free this probe from its orbit, you'll need to spend 93.6 megajoules of energy to free it. It's trapped. So it was minus 187 megajoules of potential energy. However, it does have some kinetic energy, so you don't quite need 187 megajoules to free it. You require 94 megajoules to free it. Okay? So you know what I mean by freeing it? I mean like if the probe burns some fuel to try and escape, or if you have some kind of rocket that pushes it. So like for example, if you had a rocket and it's going to hit into the probe to free the probe from the orbit, the rocket would need to have that much energy. It needs to give that much energy. So, you know, its kinetic energy, if it was pushing it, it would need to be 94 megajoules.
If it didn't, it won't fall out of the sky.
If it didn't have this much energy and it tried to free it, what would happen is it might just move to a different orbit, a higher or lower radius, you know, or possibly could burn up and fall back down. But I think if you just gave it more energy, but not enough to free it, you'll just push it into a higher orbit. That's all that would happen. So if you had 50 megajoules, it won't be enough to free it from orbit, so you'll just push it up to a higher orbit.
Or if there's some explosive things on the probe to make it explode and give it some energy to go back down.
Are you trying to get the probe to crash? Is it? Yeah. Um,
It's about the 8%.
yeah, I don't know how to answer this. What are you even asking me? I don't think you're asking me anything. Okay. Right. Wait. Before you go, I don't want to forget the things I want to change.
This question was long.
Approximately what is the total energy, kinetic and potential of the probe?
Just ask those questions could come in exam.
Oh yes, definitely. Definitely. In fact, this is a little bit like a section B question I saw a few years ago.
Last year.
No. Well, maybe, I don't know.
I remember.
This is like B6 from last year's?
You remember?
Respect to senior and
Yeah. Right. We'll stop the recording.